Today we're going to look at equations. So we're kind of switching gears from just looking at expressions to now looking at equations. Let's first talk about what an equation is. An equation would be two expressions that are equal. And the goal of solving an equation is to find the value of the variable. Now you've seen very simple ones of these before, I'm sure. Something like, for example, 3 plus m equals 5. And in something like that, the goal is to find the value of m. Now this one you can figure out really using mental math, that m equals 2. And so you've now solved that equation. The expressions that make up that equation are 3m, that's one of our expressions, and 5. And this is called an equation because it has an equal sign to show that those two expressions are equal to each other. In fact, m equals 2 is also an equation because it's showing the expression m is equal to the expression 2. So let's take a look at some examples and see if you can classify each of these as either an expression or an equation. Take a moment to pause while you try it and then hit play and check your work. Alright, if you've done this correctly, you should have something that looks a little bit like this, and hopefully you have classified each of your equations and expressions correctly. If you notice, the big key, the dead giveaway with equations is they have an equal sign, and they have an expression on each side of the equal sign. Now what I mean by that is, if I just had something like this, 7 plus 5 equals, that is not an equation, even though it has an equal sign. It's not an equation until I put the 12 on the other side of it to show that the two expressions, 7 plus 5 and 12, have an equal value. So the way that they were, those were both expressions. Now I want to further point out that I actually separated these out a little bit. Take a look and see. Everything to the left has just numbers and operations. Therefore, those are all just numerical expressions on the top up here. These are all numerical expressions. 12 minus 3, 7 plus 5, and 12 are all numerical expressions. And then on the bottom, 3 equals 15 divided by 5, 6 plus 2 equals 8. Those are both numerical equations. Everything to the right-hand side of the lines, those are algebraic because they have, that's right, variables in them. So x over 3, 2m plus 6, 3 times the sum of 4x and 7 plus 9y, m plus 8. Those are all algebraic expressions. And then down in the bottom right-hand quadrant, we have algebraic equations because they are equations that have variables. Now, let's take a moment and refresh our memory about some of our vocabulary. Make sure we know what each of the parts that make up our expressions and our equations are. So we can look at this and say, well, the x in 6x is a variable. And the 7 is a constant because it's a number. Its value is not going to change. 7 is always 7 is always 7 is always 7. And then we have an equal sign, and we're going to come back into in a minute why that's so important. And then the 3 is, yes, it's a number, but it's not a constant. It's a coefficient. And it's a coefficient because it is a number that is multiplied by a variable. In this case, the variable is y, and in fact, that y is y squared. The 2 is an exponent. But the coefficient, the 3 is a coefficient because it is a number that is multiplied by a variable. So anytime you have a number multiplied by a variable, that's going to be a coefficient. Now, if we look a little bit further and we look at the 6x, the plus 7, the 12, and then the minus 3y squared. Those are all terms. So each of those is something that is added or subtracted within that equation or within the expressions. So 6x is a term. Then plus 7 is another term. It is something that is being added or subtracted. When we look at the 6x plus 7 as a whole, so now let's go back and look at 6x plus 7, those two terms together, in other words, everything to the left-hand side of the equal sign, that's going to be an expression. And then on the right-hand side, we're going to have another expression, 12 minus 3y squared. So those are both expressions And then the whole thing, all of it together, completely together, is an equation. So my point here in this is for you to see the building blocks that make an equation. An equation is made up of two expressions that are equal. Expressions are made up of terms that are added and subtracted. There can be addition and subtraction. There doesn't necessarily have to be. And then terms are made up of variables, constants, coefficients, and exponents. Those are some of your basic building blocks. Then, so you can kind of look at this and see hopefully how equations are built. And you do need to be able to use those words properly when you talk about equations and when you talk about just algebra in general. Okay, moving on. Let's take a minute to look a little bit more at the vocabulary. Now, there's a mix-up here of expressions and equations, and I want you to take a moment to pause and see if you can match the words to the expression or equation that go with them. Pause while you do that, and then hit play when you're ready to check. Okay, if you've done this correctly, you should have something that looks like this. Now, what I want you to notice, what our key thought was here, is that the is, anywhere that you see an is, and in this case we can even go so far as to say is equal to, but anywhere that you see an is, there's going to be an equal sign. It tells you that there's an equation. And then the pieces that are to the left and right of that are to the left and the right of the is. So for example, 25 less than a number is right here. 25 is 25 less than x, is or equals 8. Now notice this one down, number 4, technically speaking, we might say you really could write 8 is equal to a number divided by 25. We're not really wrong to write it the way it was in the red there, because really those are just the same equation, just switched around backwards, and that's okay to do too. Also notice that number 2, there were two different ways that we were given that we could write that multiplication. There's other ways we could write it too, but those are just the two correct examples that were given. Something we often think about when we think of equations is a balance or a scale. And the reason why we think about that is because when we look at this, these two sides of this scale or balance, they're exactly directly across from one another. That means that the two sides have to have an equal value. So we use that image when we're thinking about equations, and we think about the equal sign being in between the two sides. So we could go into something like this. So when we look at that balance, 2 stars equals 12. So if we have 2 stars, notice that those two are going to have the same value because they're the same symbol or variable. And I could have written letters for my variables if I wanted, but I chose stars in this case, and that's okay. If you look at this, each star has to equal 6. And it has to equal 6 because I can get that a couple different ways. I can say, well, what number plus itself equals 12? And that's going to be 6 plus 6 equals 12. I could also have thought of 12 split into 2 parts. If I split it into 2 parts, each part has to be 6. That's just a couple different ways I could think of it. Now this next one, 17 is equal to 9 and star. Now you might look at this and think, well, does that mean 9 times the variable? And no, it doesn't, because think about a scale for just a minute. We don't multiply on scales. We just keep adding weights or adding things to it or taking things off it. So we can't do this as we're not looking at that as a 9 times the variable. So when we do look at this then, our star has to have a value of 8. And we could get that a couple ways. We could just guess and check and say 9 plus 1, that's not 17, so the star is not 1. 9 plus 2 is 11, not 17. 9 plus 3 is 12, not 17, and keep going until we got to 9 plus 8. Aha, that is 17. Or we could have also done, you probably guessed it by now, 17 minus 9 would tell us that our star has to equal 8. For this next one, this is a little trickier. Take a moment to see if you can come up with it, and then I'll tell you how I would do it maybe. All right, when I look at this, I would look at it and say, well, I could do a guess and check and say, could each of these be 1? 6 plus 1 plus 1 is 8. That's not going to work. Could each of them be 2? 6 plus 2 plus 2 is 10. That's not going to work. And I could keep going until I get something that does work. Or I could say, well, if I have 14 on the left-hand side and I have 6 and then something else on the other hand side, on the right-hand side, then these two pieces together have to be 8 because 14 minus 6 is 8. Or in other words, 6 plus 8 is 14 is another way to think of it. And then I can look at it and say, well, if the two stars together have to be 8, then each one of them has to be 4. And really then, this right here, I could even look at as another problem where I have 8 is equal to 2 stars. And I bet that most of you would be able to get that one very quickly and see that each star has to be 4. One more example. So 3 stars and an 8 has to equal 23, and we want to know the value of the stars. Take a moment, see if you can figure it out. All right, hopefully you got that each star has to be 5. The reason is because if I look at this, 23 minus 8 tells me that these 3 stars together have to equal 15. Then I can take the 15, split it into 3 equal parts, 15 divided by 3, each star has to be 5. All right, now another thing we need to be able to do besides solving equations is we have to be able to look and see whether any given number is a solution. So if we look at this, number 1, the directions they determine whether the given value is a solution of the equation. So the first one, 11 equals 9 plus 6, n equals 5. Or 11 equals n plus 6, rather, and n equals 5. We want to see if that's true. What I would expect to see from you if you were trying this out is something like this. 11, does it equal 5 plus 6? And put a 5 where the n was. And when I work that out, 5 plus 6 is 11. So I have 11 on both sides of the equation, which means yes, since 11 does equal 11, n does equal 5. That is correct. For number 2, y minus 6 equals 24. And I want to know if y equals 18. Well, let's try it. 18 minus 6, we want to know, does it equal 24? 18 minus 6 is 12, and 12 sure doesn't equal 24. Therefore, y does not equal 18. So 18 is not a solution to this equation. I could look at a couple more of these just to see if I have solutions or not. So 9 times 3, does it equal 36? 9 times 3 is 27, which does not equal 36. Therefore, n does not equal 3. And last but not least, 20 minus 7, does it equal 13? So let's try it. 20 minus 7 is 13. We have 13 on both sides of our equation. Think about that scale being nice and balanced. That works. So r does in fact equal 7. Another thing we need to be able to do with equations is we need to be able to look at a word problem and write an equation from that word problem. So let's take a moment and look at this situation. Marilyn has a fish tank that contains 38 fish. There are 9 goldfish and F other fish. If I wanted to write an equation to represent that solution, one thing I might say is, well, there are 9 goldfish and there are F other fish. And all of those fish together equal a total of 38 fish. And something that might be helpful when you're looking at something like this is to label it. These are my 9 goldfish. These are my other fish. So my goldfish plus my other fish is equal to my total fish. And then see, can I come up with other equations from that? And yes, I should be able to. I should be able to say, well, if that's true, then it's also true that my F other fish plus my 9 goldfish is equal to my 38 total fish. I might also realize that the total fish minus the goldfish tells me how many other fish I have, and my 38 fish minus the ones that are not goldfish tells me how many are goldfish. So I can actually come up with 4 equations to describe that situation. When you look at these, you should be kind of thinking about fact families because that's an awful lot like what you're looking at here. You're really looking at fact families. Another example. Juanita has 102 beads to make N necklaces. Each necklace will have 17 beads. Well, this one we can look at as a multiplication problem. For example, we could say each necklace has 17 beads. There are N necklaces, so 17 beads per necklace times however many necklaces I have has to equal my total number of beads. Or the number of necklaces I have times 17 beads in each necklace equals 102 total beads. Now, if you think about it, what operation goes with multiplication in fact families? You're right, it's division. So think about my divisions here. 102 beads split into groups of 17 tells me how many necklaces I can make because each necklace has 17 beads. And I could also say 102 beads split into necklaces, however many I'm going to make, tells me that I'm going to have 17 beads on each necklace. Now, something you also need to be able to do when you look at these is you need to tell what it is that the variable stands for. So in this case, 17 is the number of beads on each necklace, 102 is the total number of beads, and N equals the number of necklaces we're going to make. Matthew has read 46 pages of his novel for ELA. Kendrick has read 17 more pages than Matthew. Write 4 algebraic equations for how many pages Kendrick has read. Be sure to tell what the variable stands for. Solve one of the equations. So it says Kendrick has read 17 more pages than Matthew. So 17 pages more than what Matthew has read is equal to what Kendrick has read. That's what that statement says. So now I'm going to go back and fill in any numbers I know. Well, 17, of course, we know. Plus, we know how many pages Matthew has read. He's read 46 pages. And that gives us the number of pages Kendrick has read. And I'm going to use K to stand for that. Now, I could write 4 total equations to go with that. Now, this first one doesn't count. That was just what I was using to help me figure out how I'm going to set my equation up. I could also say the 46 pages Matthew has read plus 17 more is equal to how much Kendrick has read. Furthermore, I could say Kendrick's number of pages minus the 17 extra he has read tells me how many pages Matthew has read, which is 46. And I could say Kendrick's number of pages minus the 46 pages that Matthew has read tells us that Kendrick has read 17 more pages. So I could write those 4 equations. And if I wanted to solve them, I haven't really talked about really how to solve equations yet, but this one is a really easy one to solve. That one you should be able to solve. 46 plus 17 is going to give me 63 pages. So Kendrick has read 63 pages. And we do need to point out that we do know what the K stands for. K is the number of pages Kendrick has read. So hopefully that gives you a good start on looking at about the vocabulary, looking at the vocabulary of equations, looking at some ways we might consider solving